Sorry, yes, so now we're going to get started with the afternoon session. And I have the pleasure to introduce our speaker, who is from Yole, and I'll let her introduce herself to you. So welcome back to the afternoon session.
Okay, I have it. Normally I'm all set. All right, so I think you can hear me well. All right, so let's go for this last half day. We're nearly there, but it's a pleasure to be here. So my name is Claire Troidec, and I will introduce you to some of the market for these SiC power GaN devices. I must say, after having seen all the presentations from the beginning of the workshop with some very detailed information on the research, the complexity of making these GaN and SiC devices work, you will find this presentation really more on the high-level view and not going into too much details, but that's more or less the requirements we've got to really guide you through some of the applications, the players, so not too many technical details that could be for other discussions which have been done already. All right, so let's start. Okay, let's see if that works. Should I be pointed somewhere?
It's one of the white.
Yeah, but I am pressing the buttons.
Maybe low battery.
They were switched this morning.
Yeah, this morning was working when we tried. We'll see. No more batteries, maybe. So we needed to have a technical problem, so here we are. Yes, there's always one. So. Yes, I'm honored. No, but otherwise I can just guide you and say when we move forward or. Otherwise, I can just guide you and not use the thing now. Oops. Let's see. It does. Okay, thank you. All right. The mic is on. Okay. All right. So we should be good this time. Apparently, my PDF didn't help. So sorry for that for the organizers. Well, it's a pleasure to be here. Thanks, MITEC, for having put together this nice program with all these people. I think it's very rich in terms of interaction, technical discussions. So let's just continue for And it's here it is, it's working. So before guiding you through this market for these power SiC, power GaN devices, I would just wanted to have a few words, very general, again on power electronics. As all of you are working in this field, I'm sure you're pretty aware of that. But what I really wanted to stress out when you look at power electronics, it's really the diversity of applications that you have. So from very low power levels, where compactness will be very key, integration, of course, will be very important. And when players are looking at some lower cost technologies, so here we are talking about white goods, some power supplies, some consumer applications. And as you know, we can go into some medium level power applications, so electric vehicle, motor drives, so a big market, half of the market for power electronics is for these motor drives, some charging stations, and there you start to have this reliability, importance, and thermal management, because we will be having higher power levels, we will be talking about power modules, so for sure getting the heat out of the power modules will be very important. So that means looking at packaging technologies, materials, so the requirements will be a little bit different than the low power level applications. And then when we are going into these very high power levels, so we are talking about rail, we are talking about grids, some energy with wind, then this time again reliability will be very, very important, and thermal management again will be of increasing importance. So that was just to highlight really the diversity in all these applications when it comes to power electronics, meaning it will have different needs for the suppliers when it comes to devices, when it comes to modules, and when it comes also to the cost of the solution. So performance cost trade-off, as you know, is always a big equation, and particularly I would say in power electronics. Okay. We've seen this plot also. I don't want to spend too many time, but just to say that again, so we have a very rich application environment, and in terms of technology offering, we also have a lot of different technologies on the table to really fulfill the demand for all these power electronics applications. So we've heard some discussions on the bipolar thyristor. We didn't hear that much more mature technologies for these high power needs. Today, players are looking at IGBT or MOSFETs. A simple way of putting this together, we say IGBT are very much inclined to address the high power levels, while the MOSFETs, junction MOSFETs, are very good in tackling these higher operating frequencies. And that's where you would have some sweet spots for this new innovative technology, disruptive technologies, this wide-bandgap, silicon carbide and gallium nitride. So silicon carbide addressing more these high power applications, while gallium nitride would be more inclined to, or would have more advantages for this high operating frequencies application. And there is, as we've seen in some of the talks also, there is a competition zone between the silicon offering, silicon carbide, gallium nitride around this 650 volts, where you could have a mix of the technology platforms depending again on the requirements for your application. Okay, the idea, of course, is to cover these power SiC, power GaN markets. One of the exercises that we're doing at YOL, where we do this market research, is to try to model, building some models, trying to understand how much devices will we need, how much value will this represent, and so on. So we are really starting from the end application, so in rail, in wind, PV, electric vehicle, looking at the needs in terms of power electronics. So what are the power converters? Are we talking about DC-DC converters, inverters? What are the topologies for each of these power converters? And what kind of devices would you need? Are we talking about silicon-based devices, silicon carbide, gallium nitride, and so on? So it's a huge model where the idea is to extract the units, so the volume of devices addressing this power electronics industry, and also come up with some market figures in terms of value. People like money, people like dollars, so what does it mean? Of course, it's a difficult exercise, so here this is what we've done, and this data I want to share with you. If you do this exercise today, we think that silicon carbide represents approximately 5% of the power electronics market value when it comes to dollar at device level. Looking into the future, we think that silicon carbide could grab like 20% of the market, while GaN could grab 70% of the market. But this is all related to the price erosion that you will see with the different solutions. So we can always debate on the progression and how much market value those technologies will reach in the future. But the idea is that we're really seeing more and more projects, as you see, more and more integration of this wide bandgap. And compared to 10 years ago, we are really seeing the proliferation of these technologies in major end system applications. Okay, so now let's have a few words on these power GaN devices. So the story with power GaN has started quite recently, if you would look at it. I mean, first power GaN devices by International Rectifier in 2010. Then we've seen a lot of movements, of course, when you need to have more mature industries, there's investment, so the acquisition of International Rectifier by Infineon. We've seen a lot of companies, startup companies, so the GaN systems, the Navitas, really pushing GaN technology, being on the road, talking to the end system integrators, trying to show the value of the technologies, and partnering with some players in the automotive industries, getting some finance round to really establish the technologies. Lately, what we've seen is really an acceleration of all these investments. And here it's a busy plot again, but the idea was just to say that players have been busy setting up the supply chain, trying to find some manufacturing partners, so TSMC being one of the big foundry when it comes to GaN. Integrated device manufacturer players also entering into the play, like the Infineon, the ST. So everybody really working on the technology and securing the manufacturing aspects. And all in all, if you would look at the investment that has been made since the beginning, it's more than $2.5 billion that has been spent on establishing these technologies and partnership through the different players. Okay, so all this is very nice, but what is it for? So I think when you have a very good technology, you're looking for the sweet spot. What is the application that will help you to enter in the market? And when it comes to GaN, I mean, the fast chargers for consumer applications, for smartphone, has been one of these enabling applications to really get some more volume and some more massive implementation of the technology within power electronics. So we all know with the smartphone that are getting bigger screens, bigger batteries, more like 5G capabilities, so they're really draining the battery down. And we as an end user need to charge our phone very often, which is why when we've seen this GaN technology, so delivering higher power efficiency, higher power density than some of the silicon technologies, and also enabling miniaturization. It started with aftermarket chargers, so the Anker, the Aoki have been the first one to really more or less take the risk, but at least to investigate this technology and implement it in their aftermarket chargers. And then we've seen Oppo, so more integrating this technology back in, so aftermarket was more in 2018, Oppo for the inbox charger more in 2019, integrating the solution for power integration, and then integrating other solutions from Navitas and so on. So we've seen more like the Chinese OEM more inclined to make this transition and take the risk to implement new technologies. And lately we've seen some charger by Apple, so for a laptop, 140 watts, addressing also the market. So there are companies supplying some possible device solutions, so the Navitas, power integrations, GaN systems, and so on. And if you look at this price per power as a function of the overall volume, you would see really the benefits as plotted here of gallium nitride compared to some of the standard silicon technologies. So this is really how it has started when it comes to more volume. If you then look at the market provisions for this power GaN market, so really more mass markets with these consumer applications, we think thanks to this price erosion for the consumer, there could be like more applications in consumer LED drivers, some also of the audio amplifier, a Class D audio amplifier that could benefit from the technology. So that's the growing market for the moment. And otherwise, you would see also telecom and infrastructure, where you would have this power supply, where you're looking for very efficient power conversion. And by 2023, there will be some new regulations, for example, in Europe, really forcing some of the telecom suppliers to consider this efficient power conversion that should drive more volume for GaN. And it's really when you look at like 5G base station compared to 4G base station, some of the numbers out there are like 5G base station would consume like 40 to 70% more power than a 4G base station. So we are all understanding why we need some more efficient energy conversion when it comes to these applications. Another area of growth for GaN would be on automotive. So a lot of players, tier ones, OEM, are busy at the moment qualifying technologies, making trials for DC-DC conversion, onboard charger, also for inverter to be seen, where silicon carbide for the moment has entered. So that's something that will come, we think, later on, but that's also another pocket of growth, possible pocket of growth for gallium nitride power devices. Okay. Now, when it comes to the market, we also like to look at who are the players behind that. So the players with the market share, so that's a market we follow on a quarterly basis. So as I said today, it started with these fast charger consumer applications. So we've seen like power integrations taking market share and growing market shares together with Navitas. We're seeing other players also focusing on industrial applications or high-end applications like EPC, transform, also gaining some of the market share for industrial applications, telecom, datacom. And this market will continue to grow, and all the players are quite busy and also benefiting from the growth, pushing also this growth. Another player maybe also worth to notice here is Innoscience, really strongly progressing as a Chinese players. Really would like to reproduce the story of the LED, really driving the cost down and having some more implementation for also wireless charging for some of the e-scooters, but mainly today also for the fast chargers with this Chinese OEM. Okay, few words just on the technology. There have been a lot of very interesting talks during this last 1.5 days. So I won't spend too much time here, but just to show the diversity of the technology offering when it comes to usually GaN on silicon or GaN on sapphire. In the past, there were a lot of debate on D mode is better, no E mode is better. I think now there's a consensus that it really depends on the application. So one or the other can really be interesting depending if you're looking at high power applications or depending if you want to leverage the low losses at the application level. A set of voltage offerings, some latest developments on the 1200 volt GaN devices. That's something maybe we could also discuss on the panel. Okay, what are the applications behind that? What does it mean? Is there a potential for such technologies? Integration at discrete level, system on chip, system in package. Packaging is also, of course, very important when it comes to these GaN technologies. You can have a very nice performance at die level. And then when you integrate that in a package, we know it's difficult to drive these devices and with all the losses that you could induce thanks to your packaging, you really have to be careful with the inductance and things like that. And topologies. We've seen a lot of different topologies out there depending on your applications where you need to consider how GaN can really contribute. Is there a topology which fits better with the performance of the device? Okay, so just to give you an idea, an outlook for the future. So what does it mean? So it really started, like we say, with this fast charger for smartphones. Before, we've seen some applications like low volumes or high NPV inverters, so very specific use cases with ISiCPEAW, but definitely the growth has come from the consumer area. And in the future, more growth is expected thanks to automotive, thanks to the power supply at data centers, also some of the DC-DC link for data centers, so benefiting from the efficiency of these GaN devices. And in the future, at the same time, we are seeing industrial markets where we can look at motor drives, some of the motor drives for the brushless DC motors. Apparently, there's some nice interest also with GaN technologies and other like welding systems, welding machines, and things like that. And possibly inverters to be seen for electric vehicle. This is also a technology which is on the table and that is being considered by major OEMs. All right. Now that we look at GaN, let's look at silicon carbide. So for silicon carbide, the story is a little bit different. As you know, everything started so historically on photovoltaics, so more of these high power applications where you would see the needs of having very efficient high power density technology. And the volume has come with the automotive markets, thanks to Tesla, who took the risk to adopt the technology back in 2018. Now we're really seeing more and more players active in qualifying, looking at this silicon carbide technology when it comes to automotive. So Hyundai has made the move, BYD has made the move. We are expecting more OEMs in the future like NIO, XPeng, GM. I mean, everybody is more or less pretty busy looking at the silicon carbide technology, but at the same time also investigating IGBT and trying to look in terms of cost perspective, advantages it will bring you at a system level. I mean, where is the equation? So the growth, as you would see here in orange, we expect definitely will come from the automotive industry. Other applications, as we mentioned, energy with PV, energy stationary storage, so really the battery storage applications. And industrial also for some of the power supply, motor drives, and so on. Okay. When it comes to automotive, as you know, there are different power converters needed, either for the main inverter or for DC-DC conversion or the onboard charger. Here, this is just to depict that the majority of the market when it comes to silicon carbide for automotive will really be dedicated to the main inverter. That's really where silicon carbide can show its added value compared to other applications. DC-DC, lower voltage applications, so there's competition there with silicon, with gallium nitride. Onboard chargers, so we've seen some interesting projects of tier 1 OEM looking into this application. But again, here there will also be some competition with the other existing technologies. Looking at the investments, so also, I mean, for an industry to come up with some reasonable market sizes, reasonable market volume, that means there has been consolidation, there has been a lot of partnership and acquisitions. So the story with silicon carbide is more the early 2000s, but with a lot of players acquiring the right technology. So we've seen ROM acquiring SAG Crystal for the substrate, the business model in the company. We've seen Infineon acquiring Siltectra, more the wafering level for a cost reduction perspective, yield improvement in the future. We've seen a lot of partnerships with Wolfspeed, with some tier 1 companies or power module packaging, really trying to address the needs at power levels, at power converters level, power module level for automotive and other applications. We've seen some movements, again, ST with Norstel, more at the substrate level, SK Siltron acquiring DuPont, so the US business, again, at substrate level. So we do see, as you've heard in the past presentations, that this substrate, having this wafer technology is key when it comes, of course, to silicon carbide. And very recently, more recently, onsemi with GTAT, again, Covo with United SiC, so we've had a presentation. And this is more or less the story which is continuing with very active acquisition and partnerships. So when it comes to silicon carbide and the promise of these huge automotive markets, all the players are really getting prepared. We see a lot of capacity expansion, a lot of announcements when it comes to building fabs, securing the supply chain. So here, just for your information, that's the main players we just highlighted. So the ST, the wall speed, on-semi, Infineon more at device, power module level, ROM 2.6, as we've heard, more starting with some wafer epitaxy, growing into more device, power modules, so really climbing in the value chain. Everyone is very active in building good fabs, in investing to be sure that they will be able to address the needs from the industry. Okay, now if we look again on the market share, who are the players, who's active? So today ST is taking most of the major share thanks to the design win with Tesla. And that's something we're continuing, also addressing BYD needs. We're seeing also progress from Wolfspeed, of course, also active in some of these industrial but also automotive applications. We've seen increased growth of Infineon also entering into play with some of these Hyundai design wins, so automotive serving automotive, but also industrial high-end applications when it comes to these motor drives or charging infrastructure, for example, applications. And if you would look at the different innovations, so silicon carbide, it's a never-ending story, continuing journey. So we've seen all these partnerships securing the supply chain. Now the story is about addressing the needs when it comes to 8-inch manufacturing, so to be able to serve the mass market, lower the cost. So the main players active into this field. It's not an easy task because you really need to have these good quality wafers to be able to have your device manufacturing on top of that. Other things we've seen, so wafering process innovation, as we've said, like Infineon or Disco with their Cabra technology, we're working on the wafering level, trying to get more wafers out of one bowl and increasing the yield at that level. Engineered substrates, also we've seen, so most recently, Soitec or Sumitomo Metal Mining getting the SiOx technology. So working on thin silicon carbide layer that can be bonded on different polycrystalline, for example, wafers. And recently also here in Sweden, we've seen an innovative approach when it comes to the growth of the silicon carbide wafers with KeySab. So there are different technologies on the table, and again, a lot of momentum to address the future needs and to increase the yield, lower the cost, to continue this silicon carbide as a success story for the future. I just wanted to share some few words on when it comes to the substrates. So today, the majority of the markets is being addressed with these 6-inch wafers. So this is more at the N-type silicon carbide substrates. We are seeing so the players active with these 8-inch qualifications. We've heard this gigafab, megafab by Wolfspeed. So this 8-inch is something today where we're seeing some sampling, but the volume should come more 2024, 2025, again, if the quality is there to address the needs for this power electronics market. So in terms of volume today, we are around like a little bit more than 500K units when it comes to these wafers, and it could grow 3 times again if this quality is there for the 8-inch wafers. Just a few words, technology, again, there has been a lot of things said, but I know in the past we were discussing with a lot of our customers looking into silicon carbide and say, okay, I'll take it and I'll just plug it instead of using an IGBT. As you all know, I mean, the story is a little bit more difficult or even much more difficult than that. Replacing the die will not be enough. You really have to reconsider your full power module. So it's more when we come to these high power applications. So looking at the substrates with the high thermal conductivity, so usually the switch is made from aluminum oxide to silicon nitride, AMB. Re-evaluating your encapsulation to cope with high temperature silicon gel. Looking at the interconnections, of course, you need low inductance interconnections, so switching to top lead frames, flexible foils, these copper clips on the top. And the die attach also will be very important. As you know, we're dealing with power, we're dealing with safety, delamination and things like that. So silver sintering, for example, technologies have made their way more from some high-end aeronautics applications and being used now for this silicon carbide implementation. So the future for this silicon carbide industry, so started with PV, definitely automotive driving the volumes there. Charging infrastructure linked to automotive will also help in getting more of these volumes. And then we have some industrial applications when it comes to these motor drives, as we said, the power supply for the grid, for the rail. The needs are very specific, and again, that's something which should help in driving the growth for this SiC market. Okay, we have many reports on the topic when it comes to compound, to power modules. And we're also following this market on a quarterly basis with these power SiC, power GaN players. And if you have any questions, I will be happy to answer them. Thank you.
So thank you, Claire, for this comprehensive and impressive overview. A beautiful background to the panel discussions which will follow. And I think maybe if there are questions, of course, we can go ahead. But I would suggest that we save the questions to the panel discussion and take it during panel discussion together with the discussion. Yep. Because you should expect some turmoil now, because they will come from the hotel with the refreshments. And there is something to drink, there is some fruit and so on. If somebody wants to drink beer, they can also just order it from the people coming in. I think last time we had both beer and wine. It was not so lucky solution, because people are driving home after today. So.
Before the panel could be nice.
So there were some bottles. People disappeared with a bottle under their arm, because I cannot drink now. I drink it later. Okay.
All right.
We have to rearrange a little bit also.
So, okay, so we'll rearrange.
I'm sorry, dear friends. Let's gather together and let's start, because we are. I would like to ask.
Hear me well? Yeah, is the microphone? All right. Okay, thanks everyone. So we are back here for the panel discussion. So the idea of the panel discussion is really to look at, okay, what will come next in this next 5 years. So if we look back in the previous 5 years, I mean, as we've seen some very nice things happening to this wide bandgap with silicon carbide, gallium nitride. As I said, for the mass markets, 2018 has been a year when we've seen some GaN fast chargers for accessory aftermarkets. We've also seen this silicon carbide with the automotive Tesla. I don't know if we would have bet that 10 years ago that this would happen. So the idea more is to look, okay, from now on, what will happen in the coming 5 years. And from that, so we've invited panelists from either substrate, device, module, or system integrators to provide their view on these gallium nitride and silicon carbide markets. So I know some of you have prepared slides, so I think it would be nice maybe to kick off the stage with the slides. Victor, I think you prepared some slides, yes, just driving the discussion. Maybe we could start with you. Yes, and here is the mic. Yep.
Okay, thank you. I guess you're sick and tired of hearing from me, so I will be brief. I don't know what's going to happen to me in 5 years, but I have a good idea of what's going to happen to silicon carbide, and that's the important thing. So, I did bring my crystal ball from America to look into silicon carbide and GaN. For those of you that don't have a crystal ball, Joel can give you a very good idea of what is going to follow. Okay, so what we know is for the substrate, okay, where are we today? It's labor time intensive, the growth is complex, it increases device cost substantially, and wafer planarity and defect densities can be improved. So what is the future going to hold in my view? So economies of scales will help bring the price of the substrate down, but the physical limitations of those high temperatures and this time-intensive process will not allow it to get down to the level where you see in silicon. So it's going to remain relatively expensive and a big part of the device cost. And then wafering, we're going to see a lot of innovations there. There's a lot of money to be made by bringing down the substrate costs. So wafering is a very good area. We'll keep seeing innovations. Engineering substrates, Soitec has already started. There will be other companies that will come in and try to come up with a disruptive technology to bring this cost down. And because the substrate will remain in the next 5 years to be a substantial portion of the cost, we're going to continue to see the vertical integration. And as I said before, he who has the wafer has gold in his hands. Okay, so the next one. 200 nanometers. What's going to be the situation with that? We know that it was introduced by Wolfspeed recently. So my view is that the 150 millimeter wafers are well embedded and the cost is not there yet. You have to pay a lot of money for the 200 millimeter wafer. So we will continue at the 150 millimeter for years to come, at least for the next 5 years. I expect at least 50% and even higher of devices made on the 6-inch wafer. And I think that over the next 5 years, the planarity will improve to the point that it's going to be no issue processing the wafers for device up to 1700 volts. Now, once you go beyond that and you need, 100 micron epi, the planarity will be a very different discussion. And then the other important thing is we want to basically make silicon carbide devices with higher current, similar to silicon. So we don't have to put many in parallel and go through that pain. So I think the defect reduction will continue, and we'll be at a point where we'll make devices maybe not as highly rated in current as silicon, but close. So we'll see improvements there. Okay, so the next thing I'll talk about is the fabrication. Today we know that it's most of silicon carbide is made in silicon fabs that have introduced equipment to allow for silicon carbide fabrication, and that allows you the economies of scale, and that's a very good way to keep the cost down. So that's where we are today. So quite a few sentences to read here. So processing will continue in these silicon fabs because that's a very cheap model. You need volume to bring the cost down. So you want fabs that are fully utilized. So older fabs, mature fabs, will introduce silicon carbide into their silicon lines to increase the, the fab utilization. Now, there are non-Cmos processes that are being developed, and every company out there has its own IP, and that's why, as we saw earlier today, different MOSFETs fail in different ways, okay? So some of the non-Cmos processes will become standard, like doing basically an ohmic contact, some of the metallizations. What I think over the next 5 years will not be standard, and it will be IP-based, so every company will have their own IP on that, would be the heated implantation. There's a lot of technology there. And most importantly, the gate oxide. There is a lot of room for optimization in the gate oxide, and there's a lot of work going in that direction. So that will continue, and we're going to see over the next 5 years better mobility and all this threshold voltage instability that we talked about in the morning. Ivar Lelis pointed out a lot of that stuff will go away and give us more reliable devices. New players coming in, I think they will go with the planar devices. Of course, beyond 1700 volts, the trench device offers nothing. It doesn't offer any advantage, right? Because all the resistance comes from the drift layer. So up to 1700 volts, I think that we're going to see new players, and they're going to go with a planar device. And I think that ST and Wolfspeed will continue on the planar path and not go into trench. I've talked to John Palmer at Wolfspeed. They've optimized the planar device to the point where they feel that if they were to do a trench, it wouldn't really help them. 6.5 kVs, I think in 5 years will be commercially available, hopefully by more than one suppliers. And then with respect to the foundry versus the fab, today most of the devices are made in IDMs, like Infineon, ST, Wolfspeed, and there's of course the foundry model that's very successful in silicon. Question is that going to catch on and grab a bigger share? So the complication there is if you're having a foundry and you have 10 different customers and they come with 10 different IP for 10 different steps, the logistics get out of hand pretty fast. There are ways to do it, but we're not going to see the growth in the foundry the way we've seen it in silicon, at least not in the 5 years. I think the price will be about 1.5 times to 2 times that of silicon from 3 that it is today. It will drop, and particularly with larger area devices. And this is the big thing, that the extra cost you pay for the device is offset by the whole system level and life of system. And I think more people will start to view things in that way. So for a lot of the major applications in 5 years, silicon carbide will be the most cost-effective solution at the system level. It's already, of course, happening today in some applications. Okay, and finally, of course, you need reliability and ruggedness. So there's a lot of work that's going there. Really, the short circuit time of 3.4 is an issue with some power electronics engineers. And what I see happening there is more data will be collected in reliability, like the Tesla from 2018. So that means that the reliability will be more established because it is reliable. Apart from the gate oxide, which is the big elephant in the room, it's, silicon carbide are reliable. So the improvements that will happen in the gate oxide will take care of this threshold voltage instability, which is one, of the last reliability items. And of course, the 3 to 4 microseconds of short circuit time versus 10 that a lot of power electronics engineers worry about, that will be taken care of with the fast, intelligent drives that have prognostic, diagnostic functions, so they will be able to give you that safe operating area you're used to dealing with in silicon. And last but not least, I showed this to my kids and they were laughing, so that's another story. But anyway, I do think that in the United States, we made investments in silicon carbide very early and significant investments, and right now we're processing silicon carbide successfully, and I think that story will continue. I don't see silicon carbide in 5 years or even 10 or even longer leaving the shores of the United States to be manufactured in cheaper locations in Asia. And those are some of my thoughts. I don't know if I sound like it, but I didn't have beer, so I'm sober when I say all this, and thank you again for your attention.
Thank you, Victor. Very nice, very nice. So you're touching on some geopolitics aspects. You're touching on the cost of the wafers, on the different devices, the power rating. So very good overview. Okay. I think this is setting the beginning. I know there were other presentations. What I suggest, maybe as some of you prepared some slides, would be nice to educate the people here about your thinking. So I think, Sohel, from 2.6, you also have some slides you wanted to share with the audience. So that's something we could kick in also as well. Yeah.
I was not aware that I had to prepare some slides. I already did that yesterday.
Okay.
I think the thing I can mention is that what Victor mentioned, I do endorse many of his thinking, not all of it. That I think it's not a question of one versus the other. All of them have a play. It's not about silicon carbide versus GaN. And it is more maybe against how much displacement of silicon can be done by these technologies. Definitely GaN will have a play in 600 and below. Even at that level, it will be challenged. And similarly, when you go to very high frequencies, that there again, GaN on silicon carbide comes into play. So I think there is an opportunity, whatever in all these fields, what you are doing, and the defects, the improvements, yield improvements, ability to wafering technologies and all that. We see that there will be continuous improvement driven from economies of scale as well as the growth and back-end technologies. It will be a transition. I think 150 millimeter will be there for this decade in very high volume. And 200 will start to come in, like you were showing, about 20%. I think that's a very reasonable estimate. That the challenges from a cost standpoint, the end of the day is that yes, you get 1.8, but then everything else needs to offset that. So it will be some time. So it's a great opportunity. We are very excited, thrilled. We are we are underdog, and in America, we always want to be an underdog because the underdogs are the ones who go and win the Super Bowl.
substrate point of view, and I know it's more than substrate at 2.6, it's also from the device and the other integrations. So yeah, you wanted to add something?
I hope that both you and Victor will keep in mind next time when they're preparing these slides to reflect what we bring to the party.
Oh, we do, I think. Just see where you come from and where you're heading, which is also very interesting. Okay, I see. Yeah, from Wall Street point of view, you also prepared some interesting information. I think that could be shared.
Right.
You also want to present it? Yeah. Okay.
Yeah, sure.
Yeah.
Yeah. So this is working, right? Yeah. So I would like to give you a brief overview of what we face in the automotive industry. As you know, or as you can also see from Claire's slides, that automotive is supposed to be like one of the big contributor and consumer for silicon carbide. The 200 millimeter fab that we launched 3 weeks ago is now running first wafers, and yeah, we're all looking forward to the data which is coming out, and especially on the next 5 years. So when talking to the automotive industry, there are some gaps because they're coming from rather mechanical companies, and they underestimated that they cannot get power semiconductors in 4 weeks. Yeah. So the process time is longer than the metal, and there are 3 pillars actually. So there's the timing, the liabilities, and the technologies that all the automotive industry should take care of, and especially when you now take a look here on the right hand side. So this is basically the start of production of the car, which means so there are some gaps to provide the market with material. So this is mainly coming from the communication between the OEM and the tier 1. So the OEM is providing quite late the award to the tier 1 so that the tier 1 can actually place the purchase order at the power semiconductor manufacturer. And yeah, even before, there's a long period where no commitments are done by either tier 1 or OEM, which means there's no security and actually no interest for the manufacturer to invest money based on no commitments. Which means in order to cope with all the demand from the market, yeah, so actually you need to go back here to some commitments that the manufacturer can invest early enough to build something like a 200 millimeter fab, fully automated, and to meet with the market demand. Yeah, because you have to install all the new tools, you have to order them, and you know, as I do, that the lead time for machines is not very short at the moment. Yeah, so those gaps are actually that we need to address. There are some checklists that can be done actually with the OEM to secure the demand in a couple of years. So I don't want to go too deep into details. But what we also announced together with General Motors, and they did it quite smart, we have a program which is called Assurance of Supply. So this is a collaboration between the OEMs and the semiconductor manufacturers, which means they actually save the material for the next couple of years. Yeah, they commit to a certain quantity, and then this is something where the base is given to invest and to provide the material and make sure that the material is available. So from the timing gaps point of view, we can more or less cover it with our Assurance of Supply program, and here leverage silicon carbide for General Motors' future electric vehicles. So the other gap that we see is the liabilities. So the OEMs, they always have tough contracts, also with the tier 1s, and at some point in time, because the design-in cycles are quite long, the tier 1 is getting to a point where they accept terms and conditions, which they actually should not, because it will somehow bring them to bankruptcy or commit to things they cannot keep, like unlimited liability for a system which is electrically driven and may be not their fault. And we have competitive semiconductors in the market, which means the entire industry, like gaming, communication, and industrial, so they pay the margin actually. And automotive OEMs, they try to push down the price, which means we have seen it in Taiwan. Yeah? The automotive industry, some cars cannot be delivered because some microchips are missing and to have a wireless charger in your car, and because the TSMC factory is full. They are booked for the next 2 years, and the automotive industry didn't commit to anything, so they gave all the capacity to the guys who pay also the margin, so they make some money. Yeah, which means you have to have competitive actually terms and conditions, and more or less be a partner. Don't squeeze out anything from your supplier, yeah? And try to push all the liabilities to the supplier. So be fair. Another gap actually in the industry is the technology. Of course, if you want to be a leader, you have to look into new technologies like GaN, silicon carbide, in all, in the entire car, not only the drivetrain, also all the high voltage to low voltage conversion, which means you have to look into new technology. You have to make sure that you also use the technology. Then the challenge is actually, okay, if I use the new technology, I rather have to wait for the new technology, or maybe I can get it into the system pretty quick. However, if you then go to the multi-sourcing strategy, which means that you have to design your system according to the lowest performant device, because you have to have a harmonized system, and you only get out of it like the weakest part, right? Yeah, so you limit yourself in the technology because you have to use the multi-sourcing, and you have to design the system according to the weakest link. And it's actually also not that true that you are safe with the multi-sourcing, because if you rely on only 2 suppliers, if one engine fails, the plane will fall, which means only 2 suppliers cannot actually cope the entire demand from the market. So that's why it's nice to see that all the companies invest money in vertical integration, get more crystal growth on board to supply the entire market, because this is what we need. Yeah? We cannot have only 2 companies in the market supplying the entire world. What is actually already in the market for automotive? So this is from a German Handelsblatt. For operating systems and infotainment, they already have long-term agreements with NVIDIA, Qualcomm. Here you see the companies who have the joint venture or have the commitments with those guys, and even on autonomous driving. Yeah? So they made commitments with the companies made commitments with NVIDIA, with Qualcomm, to make sure that all the infos and entertainment system is working. And also on the autonomous driving, because those were like competencies they didn't have in-house. So actually there is a way how to do it in order to make sure that we can get cars in the future. So when you would like to order an EV car right now, you rather cannot order, or it takes more than 2 years to get one. And this is simply because automotive industries in a evolution in principle, because they have been the main players in the market. They could tell anyone what to do, and now they have to wait for the devices. So those are the 3, again, that need to be addressed in order to be successful in the future. Cooperation with your suppliers, make sure that the demand is in place. Don't tie all the suppliers to a contract and make them pay for it if something's going wrong. And I think this collaboration in the industry need to be settled right now. Okay. Thank you.
All right. Thank you, Daniel. Thank you for the overview. Yep. Thank you. So there is another device player, so onsemi, I think. Martin, you also prepared some slide. You wanted to guide the audience through.
Yeah.
Take this one. Yep. Give this
Thanks. Okay, so I already introduced onsemi yesterday, so I think I'll skip through this one. And we're just repeating, we're vertically integrated, becoming from substrates to modules. And I did something very different here. Mitek sent me some questions, so I have tried to respond to them here in front of the panel. So first question, how we see the progression of wide bandgap for power electronics. And onsemi is today focusing on silicon carbide purely. We've had GaN R&D, but now the focus is on silicon carbide. Second one, about the planar versus trench. We believe in a coexistence of planar and trench in the future. We have planar MOSFET products only. We do work with trench as well, and we don't see major differences between planar and trench. We believe they may have some different strengths, weaknesses in the future. Yeah. And then about the module, we have internal power module technology and offer module projects. And challenges here are to get electrical connections to small chips that operate at very high current densities, especially in new generations and lower voltage ratings, so going to clips instead of wires, and also power cycling capability. And cost or technology-driven power modules are preferred, often due to small footprint, easy manufacturing. And on standardization qualification for modules, the way we are working, we always qualify the die in a discrete package to be allowed to be used in a module. And then there are also some module-related reliability tests in the qualification, but the main qualification is in a standard discrete package. And on the cost and yield, silicon carbide wafer is a strong contributor for the final solution. So we see improved material quality from crystal growth and epi, and also we see that improving the wafer fab technology in terms of process defect reduction and overall cleanliness, especially in the process steps that are special for silicon carbide. Here we see a really good evolution. And as the cost decrease for wafers, other cost of other processes would be more important in the final product costs. And we see that there is a trend in the industry to go to vertical integration. This is also what we do with the acquisition of GTAT combined with internal wafering capability. And then a few questions here about 8-inch manufacturing. We see 8-inch manufacturing as a clear cost reduction enabler, but the cost of the 8-inch wafer is still an important factor. And a lower cost wafer is important both for 6 and 8-inch, regardless of the fabrication method. So there is much innovation here in the crystal growth and also in the wafering techniques, wafer dicing. And the question on the yield, we do not like to call the wafer influence to device yield as a pain point, but the influence of the material quality on the device yield is still important, limiting the maximum size of chips that we can fabricate. And on 800 volt, the question, it seems to be a big trend to move to the higher voltage, 800 volt in automotive. And here we see one important challenge as silicon carbide MOSFETs are developed for lower and lower RSP. Of course, it gets tougher and tougher to meet the short circuit requirements. So here there is important development needed. This is a real challenge for the future. And then about dedicated fabs like IDMs, we believe that silicon carbide foundry fabrication will always add some extra cost because there's one more partner company involved. But it may make a lot of sense for system manufacturers if they can do design. And importance of design know-how, related question, if it can lead to fabless business model in the future. And our experience is that silicon carbide device design know-how is critical But for the technology, there is also a close link between the device design and fabrication. It is, there is a little overlap, so to say, in the working process to get things to match. So we think that the fabless business model will require quite a lot of understanding of the technology from the device designers. Yeah, so that's a bit different compared to maybe the silicon fabless of today. And then finally a vision on new SiC entrants such as Foxconn, and if they can enter the market. And that's of course difficult to tell. But one thing I want to highlight, that even a company that has a lot of resources and a lot of money to throw in, they still need to run learning cycles, and learning cycles takes months to do. So there is also a time factor. Okay, that was all I prepared. Thank you.
Thanks, Martin. Thank you. Thanks, Martin. I see the time is running, so so we had also some few slides from the integration point of view. I don't know if you want to share them now, or if you want to just explain orally. Yeah, I think it could be nice from. Yes, because you had to leave afterwards.
I have booked it. The trains were sold out, so there was just one possibility to go back today. So I need to leave in 5 minutes. I think we can skip my slides. They were not that informative. I can talk instead. But really, the general message is now that so much happening that it's amazing. I mean, micropower is in charging and battery systems. And we see applications everywhere. There is wind storing energy from windmills, solar panels, stabilizing the grid, charging. Right now we have been historically, or at least working with the material handling business. Now we see all kind of industry getting electric, excavators, transport things, trucks, cars. So this is going to explode. You don't need to multiply your production with 10. You have to multiply your production with 100, I think, because, I mean, it's huge. There is 1 billion cars on this planet, and they're all going to get electrical. So I think the future is bright. One thing one can be a little afraid of is maybe the age of the people in here and the new engineers coming. We have really, we're struggling. And I think everyone else I've talked to here also struggling. So how do we get the kids into this market and this business? I mean, it's so much fun, isn't it? Yeah. Maybe we shouldn't start to discuss Epitaxy processes with them when they're really small. But still, I think it's sorry. So that was my. So I think somehow we need to get more young people into this business area, because there is a lot to do. It's, I mean, amazing a lot to do. So we need to go out to the middle school kids and tell them how fun it is with electricity. And that is important, because we can't grow. This is one of the major limits for us right now to grow, is to get engineers and skilled technical people into our operation. So maybe we should spend as much time thinking about how to convince small kids to go study technical subjects instead of something else. So that is one really, really important thing. And final thing is about standardization. We are right now, as we saw here before, about contracts and getting components, and it's crazy. And of course, things are growing that fast. It gets crazy. Some, blame COVID, war, and things like that. But also the growth we have right now, there will be problems, and there will be. So I think standardization is important. We see on small components, we see a lot of standard. I mean, TU247 has been around forever. On modules, we have struggled a little bit. We have a lot of single source there. Even if they choose the same, different suppliers choose the same models, they mess up the pin out, so they don't fit the same PCB, etc. And I think we have seen now that you cannot always have second source, because sometimes when you choose a special component, you have to have single source. But we have contracts lasting for years, but then it turns out that the bond wire supplier of that supplier can't get raw material, and then you have to maybe find someone else. So it's really hard to rely on one source right now, even though sometimes you have to do it. But I think so if we can standardize so that you can actually choose several suppliers and qualify several suppliers, I think that is very important. And yeah, that's probably everything from me. So
Okay.
now I'm going to rush to the train. Thank you very much.
Yes, the standardization is something which comes here from this end system point of view. Last presentation, I think Ganesh, you also prepared some slides from the system integrator point of view. So I think it could be nice to share, and I hope we'll can have some time to discuss afterwards.
Yes.
Yeah, I think so. Okay. Yeah.
All right. I'll try to be brief. So Ganesh Chandramouli. Let's see. There we go. So I'm with Alstom, so I'm very pleased to hear the previous speaker that he's going by train. We like that. And we'd like to have more trains, so he could pick a later one, of course. Alstom, of course, is one of the largest manufacturers of railway equipment and infrastructure. And I represent the Swedish business here, which was formerly Bombardier Transportation until a year ago. So if anyone is confused by the name, that's what it is. So I was told to provide some figures, and so I did. And I provided you with 4 figures, actually. And I'll come back to them shortly. Because if we look at what's been said here, we see, as I said, we're from the rail business. We've done electrified mobility for about 100 years or so. And the thing is that now we see the great thing happening, that actually road and off-road mobility coming to a convergence with what we've been doing in rail. And we see that there are a lot of synergies between the businesses, which we think are quite interesting. Of course, in the supply chain, but also in the test methods, on the system integration level, which we think can be mutually beneficial. So that's one of the trends I think that we obviously will be affected by and impacted. There's also a big trend, of course, the whole electrification and transportation transformation that's going on is encompassing everything from generation to transmission to consumption. And the interesting part, of course, is that we have energy storage with batteries, we have machines, permanent magnet machines, and we have the power electronics. All of these are rather expensive technologies, but combined, I think there is a potential for a system optimization. And again, with the cross-sectorial impact, I think we have a lot of benefits to look forward to that kind of collaboration as well. Because it's going to be the core technologies that we're talking about, but it's also got to do with the enablers like digitalization, capabilities that we were talking about before with automation and things like that. And then, of course, there are constraints and drivers that we need to consider in all of this. And I'm not going to go into the details there, but I think it'll be perhaps part of the discussion later on. So, the numbers. So from a rail perspective, what I would say is this: we would want 0 RPM fans, i.e. we don't want any forced cooling. We want them to be convection cooled. So that's one consideration. We also need them to last for 30 years, which is a challenge. So that's another aspect that you need to consider from the device and module perspective. Another aspect is of course the energy cost, because there we see that we probably could get, especially with the skyrocketing energy costs that we have right now, there is certainly potential for a case to reduce losses and thereby optimize the total cost. And I would say that maybe around at a factor of 3 times silicon on a module level, we probably would have a very good cost parity, cost benefit parity. Thank you.
Thanks. Yep, it's okay. Thank you, Ganesh.
Do not feel that you are chained to your chairs now during the second part, because we have some refreshments. I don't know how you will do it, but if you move swiftly and silently, you can make around to this table and then listen to the discussion anyway. That's how we did it those previous years. It worked. But okay, I don't know.
You need to tunnel.
Yeah. All right, so what I wanted to say, so each of you had the opportunity to share what will happen in the coming 5 years. What do you see? Maybe Gerald, you didn't have this opportunity from the Infineon standpoint, so I don't know on which part you want to comment, because you could comment on the wafering, you could comment on the device level, you can comment on the modules, on the applications. What do you see coming in these next 5 years for your company?
Let me share a few thoughts. So I guess most of you, all of you have seen my presentation yesterday, so no point in repeating slides along these lines. From Infineon perspective, we believe in the coexistence of silicon and silicon carbide and gallium nitride for at least a decade to come. Therefore, we are offering all 3 technologies. We are continuing to invest into silicon. You're seeing the huge numbers of the silicon market from Claire just earlier in the presentation. So that is the market which still needs to be served. Of course, silicon carbide and gallium nitride are very important in order to keep discussions on eye level with the advanced engineering heads of our customers. But that is quite important, because basically we want to be a trusted advisor to our customers, basically teaching the best use cases for all of the technologies. I do not believe that it makes sense to put gallium nitride, for example, into a silicon socket without changing anything. Really, topology plus modulation scheme plus power semiconductor device has to come together in order to create the system benefit, which I've heard now a couple of times also from my colleagues here on the panel. So the best use case starts with the topology in mind, and then goes into the control, and then using basically the best fitting power semiconductor device. In terms of growth areas, we just invested 1.6 billion in expanding fab space in Villach. Now, last we are sold out. So with all the drivers in the market, starting in digitalization, so data centers, telecommunication, with the 5G, with the increase of basically data in the net, then the mobile applications or electrification of the car, of the drivetrain. But all these fundamental growth drivers will create a huge opportunity for power electronics in total, and especially for silicon carbide and gallium nitride. So I think we need at least 3 further fabs in order to cope with the demand which we are seeing up in the future.
Very nice. Okay, thank you. So we can expand a little bit, right, Metek, and have it in discussion, because, yeah. Okay. All right. So there are a lot of points which have been addressed, I mean, by each of you during these specific slides. A lot of points we could comment. I mean, my first question would be more on this standardization. So we know in this industry there's a lack of standardization. Is it something that you see coming that would, I guess, also ease the path for the integration at the system integrators' point of view? Do you see more integration or more forces, I don't know, to try to deliver something that could be used by the end system maker? So I guess all of you could more or less comment on this standardization. Is it something that you're working on your organization, or that will take more time because it's very complex? Yeah, I know, Gerald, you wanted to intervene on that one.
Just a few topics on this. So I think standardization is important with respect to qualification. So as an end customer, you want to ensure that basically the device is following standards in terms of how you qualify it and how you guarantee reliability and ruggedness of the device. I do not believe that standardization makes sense in terms of device concept. Here, clearly, let the better concept win. Planar silicon carbide MOSFET versus trench versus JFET. Let's see which concept is finally winning in the market. So here I'm really thinking that the better concept will make it in the market and let 3 different concepts fight against each other. Same applies to gallium nitride, where we have basically Schottky gate versus the gate injection transistor concept versus vertical GaN. So also here, 3 different concepts, and let's see who's going to make it. Anybody else?
Yeah, I agree. So there must be some standards and qualification, and as you may all know, there's the AQG, the Automotive Qualification Guideline 324. It is divided in some subgroups, which means currently there are many people working on the standardization and how to get a document, make it understandable for everyone, and also catch all the engineers that they know what to do, how to do, and so we are on the way. It will take at least a year, probably a bit more, to get this guideline really in its final stage. But I think in the future there will be a common document where we can all refer to make sure that the quality and the qualification is in line with the expectation from the device.
The standardization, it's a double-edged sword. Some areas, yes, need to be common, like wafer size, thickness, all that. We took the lead on 150 to say it should be 350 micron. Similar questions will be there to address for 200, which will happen. Then on the other side of the standardization is what we don't want is what happened in the optical field, MSA. I think these were just like a 4-letter word for all the hard work you guys do. Let a specific design win on the basis of performance. And each inverter design is different. Maybe for the consumer chargers and all those things, you can have some kind of a standard spec and all that. But when it comes to MOSFET-based specific designs, you have easy packs and all that. That can be standardized. But I think it is going to be a combination of certain baseline stuff, but then let the best of the best win in the marketplace.
Okay. Thank you for the answers. Another topic I think which is quite interesting when we look at these automotive markets. So we see 800 volt apparently is really a big driver for silicon carbide in automotive. And I was wondering at device level, is there any challenge to address this segment? Any specific things that you should do while at the moment you can address the 400 volt automotive markets? What does it take to go to these 800 volt markets, and what do you need to do at device level? So I don't know, maybe Martin from Onsemi, if you want to comment on that, or yeah.
Maybe this is repeating a little bit, but it's much easier to get the necessary short circuit capability for lower voltage rating MOSFET like 650, 750, even 900 volt. So for 1200 volt, especially as we go down in RSP, it gets tougher and tougher. And that's the thing I can think about. Yeah.
Maybe one comment from topology side. So the transition from 400 volt to 800 volt can, in our eyes, be nicely addressed by topology. The phase modular single phase PFC plus subsequent DC-DC is fitting to 400 volt today. In 800 volt, through 3-phase topologies, like basically an active front end based on P6, plus then routing back the neutral point in order to be able to charge both from single phase and 3-phase is an option. That basically creates a market opportunity for 1200 volt silicon carbide. And then you can either stay on 1200 volt level, or you go to multi-level in terms of topology and go back to 650 volt silicon carbide or potentially gallium nitride.
Okay, both on the table. Okay.
Anybody else?
Yeah.
Yeah, so 800 volt is here today, and what is also here today is 1200 volt silicon carbide and 600 volt lateral GaN from many vendors. So the bottom line is you got to compare the two and see what makes better financial sense for the power electronics engineer, for the customer. Do you want to do, as Gerald said, the 1200 volt silicon carbide solution, or do multiple levels with 650 volt GaN? And that's something that people are looking at right now, because it's something that's happening today.
Thank you. Thank you very much, guys. I know normally the panel is also the occasion for the audience to ask questions, so we are running a little bit out of time, but I would like maybe to give you the opportunity. If there is a question you would like to ask to some of the panelists, please go ahead before we end up the session. Yep.
I have a little challenging question for all of you. And the question is, at least from the automotive industry, I say that you see that tier ones have started to develop their own chip or even their own power module. And at least from automotive perspective, I can see the price of this type of a solution is completely challenging for semiconductor industries that we have, for example, both chip and even for the whole power module. How do you think about this challenge? How you are going to overcome to this challenge? If the tier one start, the big tier ones, they have already started either to make their own power module. This is the first step. For bigger tier ones, they have started even their own chip. That will be really challenging.
I'm sure you will have answers to that one.
So I don't see a big challenge as long as the wood speed die is inside the power module. Yeah, so they can do the power modules, no problem. So once our devices are in, it's no problem. Therefore, I don't see it as a challenge. As I mentioned before, we need many players in the market to cope with the demand. Yeah? And of course, there are now many companies trying to get more knowledge, try to consolidate, try to make power modules to get more and more in-house, to be less dependent from the supply chain, making own chips. But it takes some time to make a chip which works in a DCB design and a layout with a fast switching device. So I've seen many things where people just drop in the silicon carbide in an IGBT layout, which doesn't work. So there are some learning cycles for those as well. Of course, at some point in time, they will get there, but I don't see it as a big challenge. The weight is a bit changing, let's say. Yeah? So I rather see that the tier ends, like tier 2, tier 3. This could be something they should be aware of, that now the tier 1s getting more and more independent from them. Of course, the cost structure is then better at the tier 1 because the tier 2, tier 3, they don't add the margins, which means it can be a bit slimmer than before. Of course, you have to find a balance between the quality and the cost. You cannot take always like the cheapest. When you take the cheapest device with the lowest performance, you also get the lowest performance out of your inverter. So it's a balance.
I think in terms of cost, a fully loaded and fully operational factory in a semiconductor company is hard to beat. So tier ones, like Bosch, for example, still have to show this, that they are capable to reduce the cost. I think in order to compete in the market, speed, quality, and IP protection are key. And so I see this in a sportive competition. That's a better concept win.
We have examples in front of us. Look at on the silicon side. Where is the value in silicon? What is the role of the end customer as an integrator? So the value which is in the device is tied to all the IPs which come in. And it's just not because I am an OEM, I can do everything. As he pointed out, the economies of running a factory, managing an ability to deliver a high quality, consistent supply of products and have the support available. These are not trivial things that the knowledge base of systems always comes down to, and it is very much tied to the device architectures and also how we do. I don't see that, yeah, they can specify a specific design which we can do, or Infineon can do, or Wolfspeed can do, but I'm not afraid of that. It's great if they want to come in. They will just spend and waste some more money. They are better in investing with one of us.
Okay. All right, thank you. Maybe we can take a last question before we end the panel. No?
Maybe I can
Oh, you want? Yep. Yeah, go ahead.
maybe I can raise one comment or just a question. It's maybe mix of both. Look, historically, I mean, we have silicon, maybe 60, 70 years experience, very mature technology, performing very well indeed so far. Then came gallium arsenide, after 10 years maybe approximately. Then came indium phosphide, much better transport, superior performance. We go to high frequency sides. We are touching today terahertz. There is a delta of cost. So still exists after 20, 30 years of existence of silicon carbide and, gallium arsenide and indium phosphide. So maybe I feel that you are getting something better and far better. Some delta will exist at semiconductor level, maybe 1.5, maybe 0.2 or 0.3. So there will always be some delta of silicon carbide versus silicon in terms of cost. You gain more on system level and more on integration level overall. So that's my comment. Because it's not going to be a break-even, as historically we see indium phosphide and gallium arsenide with respect to silicon for very low power consumer electronics and telecom electronics. Thank you.
Very simple. Just look at the economics.
People need to hear you. Yep.
Look at the economics. The silicon industry is, what, 600 billion? Look at the gas industry and all that. So the ratio, the economies of scale will decide and determine. If you can take the gallium arsenide to similar levels, yeah, you can come pretty close to it. But the size of the wafer, 6-inch versus 12-inch, and the volume and all that which comes in, right from the very basis of substrate all the way up. It's all volume game. And the way to look at is not a price per device. Look at what is the system cost and what that solution is. So I think there is a value proposition already there. Yes, there is improvements will come, but people will happily pay that premium because they are getting a much better system solution and much lower system cost.
And for me, it all relates to the applications. Again, here we're talking about power, SCAPE, again, enabling like electric vehicle or things like that. If we look at the gas, I mean, there have been applications when it comes to 3D sensing with these VCSELs. There are opportunities with micro-LED maybe in the future, also to go to higher wafer sizes. So with all these compound semi, now we see it as enabling technologies for much more applications in the future. So I think the future is very bright. I mean, we have the mainstream semiconductor, but when you look at compound semi, now it's all over the place. Indium phosphide also discussed maybe to be integrated in smartphones, also maybe for 3D sensing. There is room for technology innovation, and for sure we'll see more of these drivers driving, so GaN, SiC, gas, indium phosphide in the future. So I think it's a very interesting moment. If you've been part of the compound semi since years, finally, I mean, we see a lot of applications coming. So I think it's a joy for everyone. Okay, so we took more time, and there will have been more questions we could have asked, but okay, I think we need to end it here. So I thank you very much for your participation, for having taken the time to prepare the slide, to give some insights to the audience, and I think we can continue to the conference session. Thank you very much to all of you. Yeah, you want to have a last comment?
I just want to say that there's a worldwide lack of trained workforce to do this work, and given that this work leads to the type of efficiency that helps with climate change, it's crucial that we bring more people and accelerate it. And when I look in this room, 50% of the workforce talent is not here, and that's women. So I'm hoping that 15 years from now, we'll be at conferences and we'll look around and at least 1/3 of the people will be women, because we need to include everybody here. So let's do what we can.
All right, I think we can end it here. Thank you for a nice comment, Victor. Can just have it. Yeah, thanks.
Yeah, people from YOL. And I would, I have a humble request to the panelists to take their chairs with them so we can restore the scene to the presentation mode.
Do not talk. You can go now.
Hello, hello. Testing. Okay. We're a bit late now, but we have one presentation from Idaka, from Shirori Idaka, and the title is New Packaging Concept, Wiring Designs from Line to Surface, and it's a recorded presentation. And yes, please go ahead.
Okay, hello everyone. My name is Shiori Idaka from Mitsubishi Electric Young. First of all, I'd like to thank all of you for giving me such opportunities. I was planning to attend the event on site, but unfortunately, it was unable to go. But please enjoy this conference. So here is the outline of my talk. In this talk, I'd like to introduce a new packaging concept focused on the interconnect technology with silicon carbide in view. Starting with packaging challenging as background, then new interconnect technology will be presented. divided into two parts, advanced wire and planar interconnections. Okay, before jumping into the technical discussion, I'd like to introduce our company, Mitsubishi Electric. Mitsubishi Electric is a global electric manufacturer based in Japan. It provides various electrical equipment and services for building systems, trains, automotive, factory automations, and so on. Semiconductor devices are one of its business. The power device business is a little bit unique in that it has internal customers and also sells to external customers. Okay, we have silicon and silicon carbide power semiconductors with relatively high voltage from 600 volt to 10 kV and offer modules with them for various applications. We are also active in the development of silicon carbide. We began chip development in 1919, started mass production of module in 2010, and have released various modules in the market system. We'd like to explore further possibilities of silicon carbide through innovation in device technologies and ideas from user side. Okay, let's start. Here is the S-curve of power electronics as proposed by Professor Kohler from ETH Zurich. In the 2010s, power electronics 3.0 occurred with the coming of wide-bandgap. Advanced packaging is considered one of the key technologies for the next coming power electronics 4.0. So, what is packaging? I assume that the role of packaging and the structure were introduced by Professor Nielsen in the tutorial of Sunday. So I will not say much about it. There are four main roles of the packaging: to protect the semiconductors, to make electrical interface to external systems, to modularize the functions, and dissipate heat. Okay, I will skip it. From a technical point of view, packaging technologies can be divided into four domains. There are die bonding, there are interconnection, insulations, and encapsulations. In each of domains, new technologies are being considered for wide-bandgap devices. In which today, I'd like to discuss on interconnection technology. As you know well, aluminum wire were used for interconnections in power modules. Their wires are solid-state bonded by ultrasonic onto aluminum layers on the chip surface. Under operations, heating and cooling are repeated. And thermal stress occurred between the chips and wire, which has different coefficient of thermal expansion. Then cracks along the interface from the bonding edge. This degradation of the aluminum wire usually decides the life of the power module. One of the advantages of silicon carbide is its ability to operate at high temperature. Taking advantage of this, higher junction temperature, such as 175 to 100 to 155 degrees Celsius, is being required. However, more than 150 degrees Celsius, aluminum could recrystallize, and the crystal becomes larger, resulting in strength drop. In addition, because of the larger temperature difference between on and off, the thermal stress is also greater. Then significantly shorter the life of the wire bond itself. As countermeasures, new wire materials and new structures are being considered. Okay, first let's look at advanced wires. Aluminum alloy, which prevent recrystallization at high temperatures, and even copper are considered as candidates to replace aluminum wire. And the ribbon shapes are also considered in order to increase the bonding area. But all of the candidates, the material itself is tough, so damage to the chip and wear of the tool can be critical. Another challenge is the metallization of the chip. Here is a result of one experiment. Conventional material and wire structure is A. Only wire material was enhanced, is B. And metallization and wire material were enhanced, is C. This graph shows the wire bond strength after heat cycles. It may surprise, but B, which is replaced by enhanced wire, decreased in strength more than A, which is conventional ones. Post-analysis shows that B has broken within the metallization layer on the chip surface, not the interface. Because of the high Young's modulus of wire, large thermal stress generated at the interface, and it's assumed that it was broken in the softer and softer aluminum metallization layers. Therefore, in C, where the metallization layer was also enhanced, the strength drop was improved compared with A and B. This C has power cycle life 56 times longer than conventional A, with TJ max 175 degrees and delta T 100. We found that to apply enhanced wires also required enhanced metallization on the chip surface. For the metallization on the chip surface, replacement with copper has been proposed. But many process and reliability challenges remain. As the intermediate counter, we have adapted the additive method onto the existing aluminum metallization. For example, there are 3 methods: electroless nickel plating, electroless copper plating, and attaching copper foils. But it has its advantage and disadvantage, and should be used according to the specifications. Let's next, we move to planar interconnections. Planar interconnection has been considered since 2010. There are some types of methods. One is additive method, such as CMOS, SCAPE with lithography processes. And the other one is to put a flexible substrate, such as semicrons skin technology. And we, Mitsubishi Electric, have DLB, direct lead bonding technology. TPM products has been commercialized, combining with epoxy molding and thermal conductive insulation sheet. As shown in the cross-section, chips are bonded directly onto the heat splitter. Insulation sheet is installed below them. Copper lead frames are soldered directly onto the chip surface, and they are molded with epoxy resin. TPM has many advantages. First, the chip is mounted directly onto the heat spreader, and then insulation sheet with high thermal conductivity is inserted below it, thus reducing the thermal impedance of the junction to case. In the DLB structure, copper lead frames are soldered directly onto the top surface of the chip. So the self-inductance and the resistance of wiring are smaller than those of wire connections. And the heat spread on the chip surface can be improved. In addition, when chips are connected in parallel, there is no difference in wiring length, and thus current sharing can be improved. I can say this is also benefit for silicon carbide chip layer. When DLB are applied to conventional module, in which chips are mounted on ceramic substrate and gel encapsulated, the thermal stress are significant and can cause critical damage onto chip. By balancing the CD of the mold resin and insulation sheet with those of the coupling, TPM can reduce the thermal stress and warpage of the module. This results in a much longer power cycle and thermal cycle. Thus, the TPM products have a successful result in the automotive market. Now we are working for further improvement of take advantage of silicon carbide, advanced DLV, and advanced thermal conductive insulation sheet, TCIL. As advanced DLV, we propose DPB, direct power board, which utilizes PCB instead of lead frame. The board allows for stacked patterns, which reduces plastic inductance and increases design flexibility, allowing for a variety of topologies and layout, as well as additional components like sensors, passive component, and so on. And as an advanced TCIL, we propose the integration of stacked TCIL and cooling systems. This structure reduces the plastic inductance of the module and also lowers the thermal impedance junction to case. It achieves higher integration due to layout flexibility. Let's summarize my talk. Here is a summary of my talk. We try to propose further new concept continuously and looking forward to feedback from you. Thank you very much for your attention. This is my email address. If you have any questions and comments, please send the email to me. Thank you very much.
The next presentation is Elena Barbarini from System Plus Consulting, and the title is Technical and Cost State of the Art of Silicon Carbide and Gallium Nitride GaN Power Devices. The floor is yours.
So hello everybody. So this is the last presentation, so I hope you still enjoy it. So thank you for the invitation. And so I will present, so System Plus Consulting, we're part of your development group, and actually we do technical analysis, reverse engineering, and cost analysis of semiconductor devices. So I will present a state of the art of technology and cost, and obviously I focus on silicon carbide and gallium nitride here. So this is your group. So maybe I will repeat something that you already heard many times in these 2 days, but I will summarize a bit since I will talk about something that it's available in the market present, but from a technical and cost point of view. So I will make a really short introduction, then I will focus on silicon carbide, gallium nitride, and then I will conclude. So, as we already seen, this is the mapping of the topology of device that we can find on the market according to the operating frequencies, according to the switching power. And as everybody knows, silicon carbide, you can, there's the positioning for certain power mainly, and gallium nitride for some certain operating frequencies. So what I want to highlight here a bit, it's in my presentation, it's the competition between silicon, GaN, and silicon carbide. So mainly 650 volts, but I will present also the other voltages and the other electric performances. So what I want to highlight is that. So already Claire presented the market evolution. What I want to highlight are the drivers and the booster of the market that actually has an impact also on the cost. So mainly the application penetration, so where you can put your device, the efficiency, obviously, and the reliability, the cost,
of the device. But I think that's mainly now it's important to take in account also the economical, political situation. The COVID so actually has a big impact on everything, from the shortage of the component, from the lockdowns that actually multiply the shortage, and green impact, so the tendency, I mean, likely for the government and for everybody to move to a greener and more sustainable market. So I want to also to focus on EV. So we have seen that electric vehicles are the main pusher for silicon carbide mainly. So my slide is on electric vehicles, but so it's mainly for silicon carbide, let's say. Gallium nitride, obviously, we have seen on board charger. We will see on board charger. On wireless charging, so on the board of the car, not in the propulsion parts. So that's why I focus my slide on that one. But for GaN, then we have considered the power suppliers, the data centers as main driver. So let's focus on silicon carbide. So just a bit history of the devices, not of the merging, but really of the devices that come in the market, like commercially available devices. So Rome and Wide-Speed were one of the first one. They will continue with nice results. And Rome actually enter with the planar generation, but really fast switch to trench one. And it will continue to improve the new one. I will show you the fourth generation of trench of Rome also. Wide-Speed is still on planar, but we will see in the next future. And then there are, so ST, Corvor, other players, they present their devices. And as we already see there, the market is flourishing and moving. In terms of supply chain, so here is a mapping of the supply chain, actual supply chain. So from the supplier of substrate, who is playing with who. And what's interesting to see, it's who are the main revenues. This is data from Yole Intelligence. So who are the main revenues in 2020 on silicon carbide power devices. So what's interesting to see, it's actually the main players that they have the main revenue. They also have almost full, they cover almost the full supply chain. And then other players that obviously has less revenues, but because of also maybe different type of devices and less connection or less market agreement with the big players in automotive, for example. So this is the state of the commercial available device. So mainly device that you can buy yourself. Okay, if the shortage doesn't stop you and you don't have to wait many months. But so this is a available device that you can find. I put some discrete and some modules. So and also the automotive qualified. So here you see that the trend is continuing. At the beginning, and 4 years ago, there were just few 1,200 volts devices and some 600. Now we are flourishing on 1,200 volts. Some players that has Gen 6 that proposed the 3,300 volts discrete. And more and more companies are obviously automotive qualified. In terms of modules, since we are going to higher power, also the voltages are mainly 1,200 and 1,700 volts modules. So in terms of technology, this is a mapping of the cross section of devices that we could open and analyze. So here you see the design of the different design proposed by players. So they mainly the planar device. As you see, the structures are quite similar. except Toshiba proposed the integrated Schottky barrier diode in the device itself, so between the two gates. In terms of trench, so we have ROM and Infineon, and here you have the 4th generation trench from ROM. So actually, they increase the depth of the source to increase the performances and actually going down to the bulk of the device. We will compare also the performances. So we will have a look. We want to have a look also at the performances. Obviously, this is a data sheet. We don't test, so the measurements sometimes are not perfectly the same. But here so we compare the figure of merit, the SunQ by QAG. So here you see the performances of planar trench, and I also put the JFET from Genesic, for example here. And in terms of Edison per area, that's quite interesting for the silicon carbide, and you will see also in the packaging. So again, the trench, that's quite advantage in terms of reduction of the surface. So when we go finally to cost comparison, so here's the state of the art. So is the cost. So as you say, the cost, it's not fixed. I mean, the cost can change. You will have a vision of 1 year, but the cost change also, and especially now with the let's say the political, economical situation and the shortage and the supply chain, the shortage of material and so on. Also, the cost can change. But this is what we analyze right now in terms of cost of different components. So we compare the ampere cost for different voltages. So we compare mainly, so in terms of silicon carbide, we compare also 1200 with and 650 volts between IGBT and MOSFET. So why the cost of silicon carbide it's higher than silicon? Okay, we already said a bit, but so here it's our analysis of which are the factors that impact the most the cost of devices. So from what we see now, mainly it's the losses and the epi wafer cost. So here it's a total wafer cost, so it counts also for the front side, back side, so not the packaging. And if we go look at the AP wafers, so we can split the cost from the raw wafers. So we put in the AP wafers the Epitaxy cost and then the margin and the yield losses. When we talk about the potential of going to 8-inch, so here I make a simulation of the cost evolution between 4 and 6-inch. So it's obvious that if you increase, like for silicon, like for other devices, not in power electronics, but if you increase the wafer size, you decrease the cost of the device because you save cost in terms of board of the wafers and scribe lines, and so the advantages in going of 8 inches obviously to decrease also the cost, but then the problem we will see the losses, the yield losses, even if and the substrate. The fact is to see how much it costs the substrate. So finally, which is the advantages in terms of die cost at the end. So just a small presentation of the packaging. So packaging, it's as already presented before me. So it's really important. I didn't put a cost analysis of packaging, but I wanted to show some examples of real devices, mainly in automotive. So discrete packages are there. Some let's say older packaging also are still there for many other applications than automotive, like photovoltaics, industrial application. And then in automotive, you see a flourishing of solution in packaging. It's quite interesting, the trends of going to molded. So the standard packaging is still there with adaptation. Moving from aluminum wires to copper clips, also in modules, and then the molding. So here you have an example of the fuel cell of Toyota Mirai 2. So actually, this is the solution. So for now, Toyota actually just changed the die. So the module is the same, the size is the same, because actually the cooling system, if you have an idea about which one, but it's with slot, it's the same. So the first steps that they do is they change the die size, they substitute silicon with silicon carbide. And the ST, it's a quite innovator. They propose the discrete module between the two for Tesla. And now they're working on more modules. So they integrate, in this case, for example, they integrated the 1206 MOSFET, all the same size. So actually, we're 16 die inside the modules, and it is used for automotive inverter. So that was for the silicon carbide. So for GaN, I make a bit the same history. So here you have the bit of history of players. So gallium nitride was faster than silicon carbide in terms of entrance of the market after the period of research and development. We have seen the boom of gallium nitride with the entrance of actually power suppliers for smartphone, because it's the biggest market. Actually, it's consumer market. I have to say at the beginning that the suppliers are quite scared to say that they were using GaN. Some players, like Power Integration, they didn't like to said, okay, we use silicon, and actually they were already trying to use GaN to show the potential. And then now we can find the gallium nitride in charger, like standard charger for smartphone. So here I show you the players by revenue. So Power Integration was on the first one. Power Integration, it's GaN on Sapphire, not GaN on silicon, but it's still GaN-based device. So again, the supply chain. So here I put also the system where the devices are integrated. So this is the supply chain of gallium-based device. So as you've seen, it's much more complex than, let's say, than silicon carbide. There are less people there are much more pure designer, and less people that has the complete supply chain. But the advantage is to use a fab of silicon, actually. And in terms of system, it's quite interesting because you have systems so for consumer, industrial, and automotive integration. So again, the identified GaN transistors in the market. So here again is the device that you can buy. So the small voltages have a quite a long history. They are currently used for LiDAR, for example, for data centers. EPC actually is the strongest in this part of the market. Then you have all the players, 650 volts. And then there are some players that actually offer on the market the 1200 volts device. So here I put also the type. So already Claire presented, but actually when we open the device, we have seen the differences. So here I put the different integration. So there are really many choices. You can have just the power device. You have the power IC, the driver. It's integrated in the packaging. So there are really a lot of choice, and again, mainly depends on the application. Use the device in charger. Mainly the driver. It's integrated. And so the technology, so you have the technology choice of again, you can have again different options. So the substrate, silicon, sapphire, bulk, it's R&D, D-mode, E-mode, the type of voltages, obviously for different applications. As I say, the integration, so discrete, system on chip, system on packaging, sorry, and then the type of packaging and topologies. So if we go, first steps is the epitaxy. So here I show you there are mainly three types of epitaxy. So epitaxy is the most important part for gallium nitride because it's where everything is going on in terms of stress and the performances of the device, because actually you have to control the growth of the epitaxy to optimize the performances of the substrate, since you grow aluminum nitride on silicon or on sapphire. So we have three options, let's say, sapphire, let's say superlattice structures here. So different levels of concentration of aluminum gallium nitride and gallium nitride, or you have bigger layers of aluminum nitride, again with different concentration of aluminum. So I want to highlight the epitaxy because again it's the highest cost for a device. Obviously sapphires, silicon has the same cost of a silicon that you use for other applications. And so the epitaxy actually is the higher cost, and still the yield losses at the end. So here I want to also make some simulation about what happens if you use other substrate, like so sapphire you have here. It's quite interesting, sapphire, because the substrate it's a bit more higher than silicon, but actually since the sapphires the mismatch, it's much more closer to gallium nitride. You have a thinner, you can work on with thinner epitaxy, and then you have gallium nitride on SiC. So here we go back to the problem of the cost of substrate of silicon carbide, and then you have GaN. So completely vertical integration of device if you use GaN substrate. So again, the device design technologies, D-mode or E-mode. Here you have some example of the structures of mainly I highlight the gate because it's where everything is happening. So P gate or gate injection. Gate for different players, and then you have the type of the integration. So D-mode needs so mainly it's cascade, so you need a MOSFET that keep the device off. Packaging integration, as I said, many options. The beginning. Standard TO220, and then there is optimization. So gas system enter the market with the PCB embedded solution. EPC, their main market is for wafer level packaging. They do power IC or just also power device, also with multiple switch. And then you have players that prefer to sell a complete solution with a driver. And players that prefer to just sell the discrete with or without packaging. So performances, so in this case I wanted to compare the performances of GaN versus the performances of superjunction, because superjunctions are still there. So as I said, Infineon in his presentation, they are continuing working on that. It's not finished. But yes, if we just compare the design by Kuji, it's the GaN has a nice progression in terms of performances. So again, the cost comparison. So here's some example of cost, ampere cost per device per voltage. I want to, so I highlight the different packaging, because actually you cannot compare really the cost of a discrete with the cost of a complete package solution, so system in packaging or a system on chip. And I wanted to put here now the cost of of silicon and superjunction, mainly at the same voltage. So that was my last slide. So just to conclude, so silicon carbide, as we've seen these 2 days, it's there. It's now the majority of people working on reliability, so it's good, it's stable. There will be still obviously improvement in terms of performances, in terms of cost and cost driver, how we see substrate and mainly substrate and yield. For GaN market, so GaN market, the growing, it's mainly thanks to consumer application, to the entrance of in power chargers. So Apple, the choice of Apple or Samsung to go to GaN. We have to say also that the shortage of silicon maybe push also the players like Apple or Samsung to find a new source and find also, so go to main GaN players. And we will see when because we expect actually that the cost, or at least the price of silicon will increase, and it's already increased, and will be a bit increased in the next years. I say cost and price because we always have to differentiate the two. And then for GaN, we will see if they will be qualified. So when I presented my first slide, the qualification of automotive obviously was not for the traction inverter, the qualification, and for the GaN, so there is R&D for the traction inverter, but that we will see. And I say that there is no defined technology. So at the end, it's a bit the conclusion that we already heard, but the choice of the device depends of your application. The improvement it's there, and yes, we have to consider always the economical and political situation and what's happening everywhere in the world. So again, the moving of fabs from Asia to Europe also, and so on. So thank you for the last minutes.
Do we have any questions?
First, thank you for a very good presentation. I have one question about the way that you have categorized the suppliers. You have put a graph to show that which supplier is, for example, much more provider for the silicon carbide or gallium nitride. But we know also these suppliers provide for both industry application and automotive applications. I think it would be good that you also have such a curve to show
who is going where.
Yeah, first in the, for example, automotive, in industry levels, that we can understand that which one are more active in that area. Mm-hmm. Because now we are comparing of them is a little difficult.
Okay.
And my second question is, what do you think about the 1200 volt GaN? If it comes to market, can it be for example, role player to change the market?
I don't think so. So as I show you, some players propose it, so you can buy and test. So they play. So I didn't show you, but actually they play on the design. They don't play on the epitaxy, moving to 1,200. I cannot test it. I don't have ability to test the qualification. So from a cost point of view, are competitive because the cost is not so high respect to 6,500 because they use the same thickness of epitaxy. Then the problem is the reliability of that device and the strength to high temperature. So if you compare with silicon carbide. So what the advantage of going silicon carbide is also to keep higher temperature in the traction inverters. So and then what's the interest of going to high frequencies in the traction inverter? That's also a question to point. So for me, it's a nice exercise for them also to show the capability to go to this voltage. Then we have to see the real integration and also the design, because what I heard it's that it's better demode for 1,200 in a high power application. So then you have to see also the integration in a module. So that means that if you put the driver inside the modules and not outside the modules, so that means that the system designer have to change everything, or at least they change. So again, from a point of view of what's happening, the final cost of the system, it has to be studied, let's say, because it's silicon carbide, let's say, was much more easy to change, to switch, but gallium nitride, you have the problem of the driver, especially if you use a demode. So maybe for consumer.
Thank you very much. Thank you for your complete explanations.
Propose we give an
Thank you.
Okay.
Okay. Last presentation is going to be closing remarks from Professor Hans Petterné from KTH.
So it's 16.25. That means I have minus 5 minutes to conclude this conference. I prepared 7 pages of notes here, and I can throw them away. I just want to first thank MIATEC for his great efforts in organizing this event. And and I'm so happy that we could have an on-site event this year. This makes all the difference, and I hope that it has been as valuable for you as for me to meet all people here again, because I'm sure those contacts we make here will make a difference in the future. So, as I said, I prepared a lot of comments of what have been said here today, but I can't comment on that in a few minutes. It has been fantastic, a lot of really good presentations, and I would like to thank all presenters for that. Now, I would say also a few things about the event itself. We have had 103 on-site participants, and we have had 27 speakers, and we also had 6 online speakers here. So this shows that this is really a living community, and I think we can maybe have an even better event next year. So I wish you all welcome. Do you want to say something? No? So I wish you all welcome to next year's event, and have a nice time until then, and make sure that Wide-Bandgap is growing even more. Thank you.